Okay, it's time to get us a little bit of lesson number 3 here. This is all about, you guessed it, tangents. Here's what we know so far, that the tangent of an angle is equal to the opposite side length divided by its adjacent side length. That is the TOA in the SOHCAHTOA, so to speak. This is a little bit different. We're actually going to talk about tangent as how it relates to geometry, not just trigonometry. So there's a little more to the story here. So we're using this, oops, God, what the heck was I typing this morning? We're going to use the relationship between tangents of radii and circles. That's just wrong. But along with the trig definition of tangent, so we're solving problems with missing sides and angles and these relationships. So once we get started, the first part is looking at this idea of distance. So the distance from a point to a line. Diego says, no matter where I put point D, CJ is always going to be the shortest path. And he's right, because point to a line, point to a line, point to a line, point to a line, the shortest distance between any point to a line is always the one that makes the right angle. So that's really what's going on here. So Diego's kind of investigating this a little bit, and we're just going to take his word for it that, you know what, when you hit that line at a right angle and you make a perpendicular line, that is the shortest distance. So that's what he's really saying there, is that these two lines are perpendicular. That's our first idea. Perpendicularity. No matter where we put that point, the shortest distance from a point to a line is perpendicular. So you can make a note here, say in your notes, quick note to self, the shortest distance between or from a point to a line is perpendicular, and we like this symbol, perpendicular. And we take that knowledge and we move on to the next step. We say, okay, well, that's great. What about when we put that line into a circle? In other words, if you draw a radius here and then you make a line that is perpendicular to that radius, so then you draw that perpendicular line right here. Well, you'll notice that oops, that's not the best perpendicular. Let's go a little better on the perpendicularity there. Let's get a little closer. There we go. That's a little better. We're noticing that that creates a 90-degree angle. 2 90-degree angles, actually. So right where that meets, you've got a 90-degree angle, and that's going to happen anywhere you draw that line. If you draw a radius down here, and you draw a perpendicular line, you draw a radius over here, you draw a perpendicular line. But the main big idea here is that it intersects the circle at one point and one point only. And it makes that word intersects the circle at that one point, you created a bunch of perpendicular situations. And that is what we call a tangent line. So that line has a name. Even though you know tangent as a trig function, we now can say that is actually a tangent line. It intersects the circle one time, and it makes a right angle with that radius. That's what a tangent line is. Now let's go a little bit beyond that and say, okay, ready for more? Here's the more part. The more part. Once we do that, we take this is a radius here in a circle, and the radius there is 1, just so you know, and the angle is a 50-degree angle. That's a central angle right there. And it intersects this line in 2 places. It actually hits this tangent line on the circle, and that's where the right angle is, because that's what we just kind of mentioned. But then it also intersects the circle out here outside. It hits that line twice. So it does hit the tangent line twice if you extend out from the radius. But we do know that the radius is 1, so there's a little piece of this line right here called 1. I'm going to make a third point on the circle here. Just call it P for the moment. So the question is, what is the length of line segment AB out here? We should also make a note that we can actually calculate what is the length of this little line segment PB right there, that little piece. That's not part of this problem, but we're going to do it anyway. So when we're taking a look at this, if you were to break this out into a triangle, you would actually have a right triangle where this leg up right here, adjacent to the angles, if I just literally redrew this as a 50-degree angle right there. I pulled this triangle out and I moved it over and reoriented it. That means the adjacent side is 1. The opposite side, that would be OB. We don't know that yet. Or excuse me, not opposite, hypotenuse there. The hypotenuse is OB, and this AB would be the opposite side. So we could actually set that up and solve for AB using, guess what? The trig function. So we've got an angle here, a right triangle, we've got an angle, we've got an adjacent, we've got an opposite, we've got a hypotenuse. So we're just going to do that. That's literally what we're going to do. Just going to set it up as the tangent of 50 degrees is equal to opposite over adjacent. So side AB over 1. And by the way, divided by 1 isn't anything. It's divided by 1. So the 1 really doesn't have any consequence to this equation at all. So we're using a circle with 1. Now if it was a bigger circle, that length of AB would be obviously bigger. You'd have a different number going on there. So in the moment, we're just going to say, you know what? AB is the tangent. So if you look at this, this is like a big aha moment here. Side length AB is equal to the tangent of 50 degrees. So that side length over there, I'm highlighting it again and again and again, is equal to. Now we can actually find it. Let's do the math here. Tangent 50 degrees, that's a calculator thing. So you got to go tangent, 50 degrees, make sure your calculator is in degrees, 1.19. We say, okay, great. That's AB is 1.19. There it is right there. Gonna circle it just so we know what it is. How do we find OB? The longer side, well, that's Pythagorean theorem. So let's just move on over here to the left and say, well, then that side OB should be equal to the square root of 1 squared plus 1.19 squared. And that's using the Pythagorean theorem to find the hypotenuse when we know the two legs. So let me do a little fancy calculator work off screen here for a moment. That's the square root of 1 squared, which is 1, plus 1.19 squared. And we come up with a number of 1.55. That is the overall length of the entire side here, this long side, OB. So I'm just going to put it over here as 1.55. And then we know that if that's 1.55, it's broken into two pieces. Part of it's 1, and then the rest is the 0.55, if you will. So that's our 1.55 right there. So it's two pieces together. So we can use a trig function to solve for missing side length, but really the big idea here is that the biggest idea on the planet right now, on this little planet right here, is that that side length that connects between the point of tangent C and that central angle where it extends out to it, that length of that line is the tangent. That's what the tangent as a geometric point is represented as. So pause the action here if you need to, but we're going to keep rolling right along. We're at 8:02. Going to take a look at another little idea here. This is actually not a little idea, but if I connect, this is 3.3 here, if I connect the radius to the tangent lines, and I have two tangent lines, and you can see they actually come together here in a point, and they make an angle, right there, angle Z. Well, there's another angle straight across from that, and they ask us to call that W. So there's a question at hand. Here's the question. What is the value of W plus Z? And you may say, well, I'm not quite sure, but I do know something about this problem. I do know that point of tangent C right there, where that makes a right angle. So I know those two angles right there are both 90. So there's 180 degrees. And hopefully you remember that the whole quadrilateral itself, has a sum. All those angles add up to 360. That was an old property. You take four sides, take away 2, multiply by 180. That was an old formula we used way back. So those add up to 360. And just think of a square, a rectangle, 490 angles, 360 degrees. So that means that if that's 360 for all four, and these two are 180, that means that those other two have to add up to 180. So W plus Z has to add up to 180. That way, all four angles add up to 360. There's just no way of getting around it. So W plus Z here adds up to 180. They're supplementary. And what you could say is this. You could just say the opposite angles in an, I don't know what you call this thing. It's a kind of a tangent-based quadrilateral. It's a quadrilateral that's made up of the two central angles, or the central angle, the radii, and the two tangents. that those two opposite angles are 180. And that's just a little bit extra information there. You might want to use it to solve a problem along the way. So if you'd like to, take a look at the summary. I'm just going to draw on this a little bit. I'm just going to make a tangent line, and I'm going to make an angle here. I'm going to put that theta right there, and I'm just going to say that the tangent of that angle is side length. I need a point over here, don't I? Let's call that, I got AB, let's call that C. So the tangent of that angle is that side length, BC. And I do want to make a note that that angle right there is a right angle. That's really the biggest piece of this whole lesson. And then we go in and we take a look at a few problems here. Let's take a look. What do we got? Line BD is a tangent. Okay, so that is a tangent. So that tells us right away to make that a 90-degree angle. So I go out here and I label it right on there. So angle ABD, 90-degree angle. And then it says, why is the measure of BCA? Well, BCA is this little angle over here. Why are they equal? Well, we can actually say we know this one's 90 degrees out here because, by definition, the angle of a tangent line is 90 degrees. So we can actually write that in there. And this other one, you might think of that as an inscribed angle because that's actually what it is. It's inscribed. Here's the diameter. Here's the arc of 180 degrees. And there's the angle. It goes right through the diameter. So it's actually, the inscribed angle, if you remember, is 1/2 the arc. So if the arc is 180 degrees, the inside angle is 90. So you have a two-part there. One angle is equal to 90 because it's a tangent angle. One angle is equal to 90 because it's inscribed. Well, 90 equals 90, therefore those angles are equal. Check. Problem number 2. We've got a central angle right here. We've got a tangent, so right there I'm going to make that a right angle. This is by the way, this is where trigonometry all came after geometry. Geometry was worked on, and then they figured out, hey, wait a minute, there's some other things going on here, and that's what we're studying right now, is a little more of the trigonometry that's related to the geometry. And so here we go. We got a radius of 1. So there's a 1 there. There's a 1 here. So there's the radii. We've got another side length of 1.5. It says find the length of segment AB. Well, to do that, we're going to need to use the Pythagorean theorem again. We're just going to say, well, the whole length, AO, is the hypotenuse. And that would be 1 squared plus 1.5 squared. So I'm going to use my calculator here to calculate that. Square root of 1 plus 1.5 squared. And that gives us 1.8. So that means that that whole segment's 1.8. Take away the 1 because you take away the radius. And that means that little piece there is going to be the 0.8. That's your little piece right here. 0.8. So a little bit of Pythagorean theorem kind of works with this. You could use trig as well. You could use some trigs as well, but you don't know the angle, so it's really kind of pointless. Use the trig when you got an angle. Don't use it when you don't have an angle. And our last little piece of the homework puzzle here. Look at this problem number 3. It says technology required. By the way, that just means use a calculator. That's all that means. Use a calculator. Let's see, we got PD as a tangent. Okay, so right here, always just right in the right angle. There it is. Okay, so now we got right triangle situation. They're asking us if this outside length here of 1.2, they say the radius is 1, so there's a 1 here and a 1 here and a 1 here. Those are all length of 1, because they're all radii. OA, OC, and OD. They're asking us which one's closer. So really the focus on this is really right here. Which point is closer to point P? And you know it's not A because it can't be. Look how far out that is. It can't be D because look at way out. It's got to be somewhere right here between B and C. So what do? The same thing we just did. Pythagorean theorem. So let's find segment AP first. That's going to be the square root of 2. And I'm using 2 here because that is... You can see it down below here. That's this length, this diameter. So it's that diameter right there. That's the 2 squared. plus 1.2 squared over here, because that's, I can see that. Well, let me unhighlight it. There we go. I can see that 1.2 right there, so I'm going to use that, 1.2 squared. And I'm going to calculator this. I'm just going to run it through and say the square root of 4 plus 1.2 squared. Let's go 2.33. And then I'm going to take away the 1.7 because I don't want that. I want what's left. So I've got 0.63. Doesn't say inches, does it? Does say inches. So that right there is this side length here from P to P. So that tells me how far that is away. And then if I go and I have to do the same exact thing to the other side, that's the square root of, and this is, by the way, side length OP. Now I've got this little triangle here. I'm just going to highlight it for a second. This smaller triangle right here, if I highlight it, you can see me highlighting that. There we go. That means that is a side length of 1 squared and then a 1.2 squared. Calculate that. That's a calculator issue. 1 plus 1.2 squared. I get 1.56. And I subtract the 1 from it because I just want the smallest piece. So that's, I take away the 1, so I've got 0.56. That's the distance right here from P to C, or CP, if you will. And then the original question said, which one's closest? Well, the shortest distance is obviously going to be the closest. So really, point C is closer than point B. And that wraps it up for this one. That's lesson 3. See ya.